Shen, student ID of 132921031. Today I will present my final project on information theory application in deep learning, specifically focusing on adversarial compression for large language model memorization detection. This, this lab was conducted as part of the information theory course at the Department of Computer Science and Information Engineering at National Taiwan University. Here's the outline of my presentation. First, I will introduce the problem of LLM memorization and our research question. Second, I will provide background on information theory concepts and related work. Third, I will explain our experimental methodology. Fourth, I will present our experimental results. Fifth, I will discuss the implications and limitations. Finally, I conclude with key takeaways and future directions. Large language models such as GPT-3, GPT-4, Claude, and Llama have demonstrated remarkable capabilities and now deployed in production systems worldwide, handling sensitive and proprietary data. However, these powerful models raise critical concerns. First, privacy concerns arise because these models can reproduce training data verbatim. Second, copyright issues emerge as they may memorize copyright content without authorization. Third, there are questions about generalization, whether the model truly learns patterns or simply memorizes examples. The diagram on the right illustrates this concern. Training data flows into the LLM, but we need to determine whether the output represents genuine learning or mere memorization. This brings us to our central research question, shown in the highlighted box. Can information theoretic compression metrics effectively distinguish between memorized and generally learned content in large language models? The question matters for three key reasons. First, traditional metrics like perplexity and accuracy do not distinguish between memorization and general learning. Second, we need scalable, inference-only detection methods that do not require access to training data or model retraining. Third, this research connects classical information theory with modern deep learning, bridging fundamental concepts with practical applications. Our research has four specific objectives. First, we apply information theory by using Kolmogorov complexity approximations through practical compression algorithms, including gzip, Z-standard, and broadly. Second, we quantify relationship between perplexity compression and memorization, establishing measurable threshold. Third, we validate our approach with adversarial testing using character level noise injection, and robustness analysis. Fourth, we provide practical tools that require only inference without any training, making them scalable to real-world applications. This work makes four key contributions. First, we establish a theoretical framework that provides a rigorous connection between classical information theory and LLM memorization. Second, we provide empirical validation showing that memorized text has 60.3% lower perplexity than expected. Compression ratios differ by 11.33%, and Shannon entropy increases monotonically across categories. Third, we conduct adversarial testing demonstrating the memorized content showing 39.5 times greater sensitivity under noise perturbation. Fourth, we provide a complete implementation with a reproducible inference-only methodology available as Google Colab Notebook. Now let me explain the information theory foundation underlying our work. On the left, we have K complexity denoted by K of X, which represents the shortest program needed to produce string X. While theoretically uncomputable, we can approximate it using practical compression algorithm, so K of X approximately equals C of X. The compression ratio is calculated as compressed size divided by original size. On the right, Shannon entropy, denoted, denoted H of X, quantifies average information content using the formula shown. Below that, perplexity measures a language model's uncertainty through the exponential of average negative log probability. The diagram shows how these concepts relate. Low K complexity and low entropy both indicate memorized content that is more compressible. Our work builds on three important previous studies, all published before 2023. First, Carlini and colleagues in 2021 demonstrated that GPT-2 and GPT-3 can reproduce training data verbatim, showing that larger models exhibit stronger memorization tendencies. Second, Campbell and colleagues in 2022 investigated how data duplication correlates with memorization, finding that deduplication reduces privacy risk. Third, Lee and colleagues in 2021 proposed using compression complexity for language model evaluation, arguing that compressibility reflects learned structure. However, a research gap remains. We need to unify we need to unify We need a unified information theoretic framework with practical inference-only detection methods, which is what this study provides. Here is an overview of our experimental design shown as a pipeline. We start with GPT-2 model with 124 million parameters. We then process test text from three categories. We calculate metrics including perplexity, compression ratio, and entropy. Finally, we perform statistical analysis. We choose GPT-2 as our model because it is publicly available and well documented, computationally efficient, requiring no GPU, representative of transformer architectures, and has 124 million parameters trained on web text datasets. We construct three text categories for our experiment. The first category, shown in blue, contains memorized text, famous quotes highly likely to appear in training data, including passages from Shakespeare, Dickens, the King James Bible, and the Gettysburg Address. We use four tags in this category. The second category, shown in green, contains natural text, common but not memorized prose, including conference information, technical descriptions, general statements, and everyday topics. We also use four tags here. The three category, shown in red, contains random text, semantically incoherent but syntactically valid sentences with nonsensical combinations and unusual juxtaposition. Again, for text, in total we have 12 tags across three categories. We implement three key metrics. First, the compression ratio, calculated as the compressed size of the tag of text X divided by its original size using gzip, gstandard, and Brotli algorithms. Second, perplexity, calculated using a sliding window approach as the exponential of the sum of negative low log likelihood divided by the number of tokens. Third, Shannon entropy at a character level, calculated as negative sum of probability of character C times log base 2 of probability of C, where we sum over all characters in the alphabet. Our adversarial compression method uses character-level noise injection as shown in the algorithm on the left. Given a text x and noise rate alpha, we convert the text to a list of characters, calculate the number of changes as alpha times the number of characters, randomly select positions to modify, and replace each selected character with a random character. We test 5 noise levels: 0% as baseline, 5%, 10%, 15%, and 20%. Our hypothesis is that memorized content should be more sensitive to perturbation than naturally learned patterns because memorization depends on exact character sequences. We employ three statistical analysis methods. First, analysis of variance or ANOVA to test the null hypothesis that mean perplexity is equal across memorized, natural, and random categories. Determine, determine, determining if categories differ significantly. Second, effect effect size using Cohen's d, calculated as the difference between means divided by pooled standard deviation to quantify practical significance beyond just statistical significance. Third, correlation analysis using Pearson correlation to identify relationships between perplexity, compression ratio, and entropy, helping us understand how these metrics interact. Now let me present our experimental results. The table shows summary statistics by category. For perplexity, memorized text averaged 46.11, natural text 18.30, and random text 881.13. For compression ratio, memorized text average 0.8826, natural text 0.9824, and random text 0.9896. For entropy, memorized text average 3.93 bits per character, natural text 4.17, and random text 4.326. The key observations are perplexity increases from natural to memorized to random. Compression ratio increases, meaning less compressible from memorized to natural to random, and entropy shows monotonic increase across categories. Our first major finding is that compression distinguishes memorization. The compression ratios are 0.8826 for memorized, the rest are the same. The differences are significant. Natural text are 11.3% less compressible than memorized, and random text are 12.1% less compressible. The bar chart on the right visualizes this clear progression. The insight here is that memorized texts are significantly more compressible due to redundant patterns present in the training data. This validates our use of key complexity approximations through practical compression algorithms. Our second finding involves a counterintuitive result about perplexity. The perplexity values are 46.11 for memorized text, 18.30 for natural text, which is 60.3% lower, and 1800 at 81.13 for random text. Natural texts actually have lower perplexity than memorized text, which seems surprising. Why does this happen? GPT-2 was trained on modern internet text, so contemporary prose is more predictable to the model. Historical texts like Shakespeare and the King James Bible use archaic language less represented in training data. The key insight is that both memorized and natural text have dramatically lower perplexity than random text, confirming that the model has learned meaningful patterns. The log scale chart on the right clearly shows the dramatic difference. Sorry. Our third finding is that Shannon entropy confirms our category construction. We observe a monotonic increase in entropy. This progression reflects decreasing structure. Memorized texts are highly structure famous quotes with repeated phrases. Natural texts use standard language with typical word distributions, and random texts are semantically unconstrained, though syntactically valid. The bar chart visualizes the clear progression. This validates our experimental design. Character level entropy correlates with semantic coherence and properly distinguishes our three categories. This table shows detailed results for individual texts, revealing interesting patterns in the memorized category. The Dickens quote achieves the lowest perplexity, suggesting very strong memorization. In contrast, the Gettysburg address shows the highest memorized category perplexity, likely due to its archaic vocabulary. Natural text shows consistent mid-range values for both metrics. Random text exhibit extreme perplexity variance ranging from 300 to 1000, reflecting their unpredictable semantic content. The blue algorithm sentence achieves the highest perplexity of all text at 1000. This figure represents a comprehensive four-panel visualization of our findings. The top left panel shows perplexity by category, with random text exhibiting orders of magnitude higher uncertainty compared to memorized and natural text. The top right panel displays compression ratios, demonstrating that memorized texts are most compressible. The bottom left scatter plot reveals the relationship between compression and perplexity. Natural and memorized text show negative correlation, while random text cluster separately at high perplexity and high compression ratios. The bottom right panel shows average Shannon entropy increasing monotonically from memorized to natural to random, confirming our category validity. Together, these four panels provide strong visual evidence for our hypothesis. We conducted rigorous statistical tests to validate our findings. The ANOVA test results shows an F statistic of 7.243, one with a p-value of 0.0099, which is less than 0.01, indicating highly significant differences across categories. For effect size analysis, we calculate Cohen's D comparing memorized versus text for perplexity. The calculation yields D equals 0.679, which represents a median effect size. This means our findings are not just statistically significant, but also practically meaningful. The combination of significant ANOVA results and medium to large effective size confirms that our categories exhibit genuinely different information theoretical properties. The correlation matrix reveals important relationship between between our metrics. The table on the left shows Pearson correlation coefficient (PCC). Most notably, compression ratio and entropy have a strong positive correlation of 0.836, confirming that higher entropy tags compress less efficiently, which align perfectly with information theory. Perplexity and entropy shows moderate positive correlation of 0.532, linking model uncertainty to information content. Perplexity and compression ratio shows moderate positive correlation of 0.381, supporting our central hypothesis. The metrics capture related aspects of memorization. The key takeaway shown in the alert box is that these strong information theoretical relationships are confirmed empirically in our experiment. This table summarizes results from our noise injection experiment. At the 0% noise baseline, we see perplexity of 43.404 memorized, 22.16 for natural, and 797.2 for random text. As noise increases to 20%, perplexity increases dramatically. Memorized reaches 1,756, natural reaches 2,774, and random reaches 3,150. The total increase factors are 39.5 times for memorized, 124.2 times for natural, and only 3.95 times for random. The interpretation is revealing. The natural text showing highest sensitivity at 122 for 24 times, suggesting the model relies heavily on exact word sequences for contemporary language. Memorized text show moderate sensitivity at 39.5 times, indicating partial memorization where the model recognizes patterns even with noise. Random text show lower sensitivity because the model already treats them as highly uncertain, so noise has minimal additional effect. The figure visualizes our adversarial compression results in two panels. The left panel shows how perplexity increases dramatically for all categories as noise level increases from 0 to 20%. Natural text shown in blue exhibit the steepest rise, reaching the highest perplexity at intermediate noise level. Memorized text in red shows substantial but more moderate increases. Random text in green start at high perplexity and increase further, but with the smallest relative change. The right panel shows compression ratio changes under perturbation. Compression ratio remains relatively stable for natural and random text across all noise levels. However, memorized text show increased variability in compression ratio, suggesting their structure depend heavily on exact character sequences. This differential response to adversarial perturbation validates our compression-based approach to detecting memorization. Let me summarize our five principal findings. First, compression distinguishes memorization. Memorized text achieve 11.3% better compression than natural language, validating our K-complexity approximation approach. Second, perplexity reflects learned patterns. Both memorized and natural text show dramatically lower perplexity than random sequences, confirming meaningful pattern learning has occurred. Third, entropy correlates with category. Shannon entropy increases monotonically from 3.93 to 4.17 to 4.3 0.26 bits per character across all three categories. Fourth, adversarial validation succeeds. Noise injection shows that memorized content have 39.5 times sensitivity, demonstrating distinct behavior under perturbation compared to naturally learned patterns. Fifth, statistically significance is confirmed. ANOVA shows p-value less than 0.01 and Cohen's d equals 0.7679, validating practical importance beyond just statistical significance. Our results align beautifully with fundamental information theory principles. For K complexity theory predicts that K of memorized should be less than K of natural, which should be less than K of random. Our compression ratio empirically confirms this ordering 0.8. Sorry, I'm not reiterating all the details. For Shannon entropy, the progression from um, reflects decreasing structure. Memorized texts are highly structured, famous growths. Natural texts are standard distributions, and random texts are semantically unconstrained. For perplexity and cross entropy, the formula shows perplexity equals 2 to the power of cross entropy. Lower perplexity for natural text suggests GPT-2's training distribution closely matches modern prose, while historical text creates distribution mismatch. The diagram illustrates how low K complexity and low entropy both indicate memorized content that is more compressible. Our work enables four important practical applications. First, privacy auditing. We can identify low perplexity, high compression text segment, test them with adversarial perturbation, and flag potential memorized training data. This approach requires only inference, avoiding expensive retraining. It is also scalable to large-scale applications. Second, copyright detection. Publishers can submit copyrighted text to our compression analysis, compare against baseline natural language, and identify potential unauthorized memorization. This is quantitative method for copyright investigations. Third, training data curation. Model developers can pre-screen training data for highly compressible passages, apply deduplication to reduce memorization risk, and balance data diversity to improve generalization. This is a proactive approach to preventing memorization. Fourth, model evaluation. We can assess true generalization capabilities, compare memorization across different models, and guide model selection decisions using quantitative metrics rather than subjective assessment. Our study has four main limitations that should be acknowledged. First, model scale. We tested only GPT-2 with 122 from 24 million parameters. Large models with billions of parameters may behave differently, so we need validation on GPT 3.5, GPT 4, Claude, and Llama 2 to confirm our findings generalized. Second, language scope. Our experiment was conducted only in English. Multilingual generalization is unknown, and compression properties may differ across language with different character sets and linguistic structure. Third, sample size. We use only 4 texts per categories, which limits our statistical power. Larger sample size would provide more robust conclusion and allow for more sophisticated statistical analysis. Fourth, compression approximation. Practical algorithms like gzip only approximate true K complexity, which is which is theoretically uncomputable. While useful, these approximations have inherent limitations and may not capture all aspects of algorithmic information content. We identify six important directions for future work. First, scale studies. We should test our method on GPT-4 and Claude Sonnet, comparing models with 1 billion, 10 billion, and over 100 billion parameters to understand how memorization detection scales. Second, multilingual analysis, extending to Chinese, Japanese, Spanish, and other languages to identify cross-lingual memorization patterns. Third, token level compression, moving beyond the character level analysis to investigate compression and the subword or BPE token level. Fourth, real-world pilot, partnering with publishers or content creators to develop practical copyright detection systems. Fifth, adversarial robustness, exploring semantic preserving perturbation beyond simple character noise, such as paraphrase, paraphrase-based testing that maintains meaning while changing surface form. Six is neural compressors, designing specialized neural network architectures specifically optimized for memorization detection, potentially achieving better performance than general purpose compression algorithms. So the key contribution to responsible AI development in important ways, it enables transparency by allowing auditing of black box model that were previously opaque. It supports accountability by providing concrete evidence for copyright investigations and privacy audits. It, pr- it protects privacy by defending individuals from data extraction attacks, and it builds trust by helping users understand model capabilities and limitations. The stakeholders who benefit include model developers who need to audit their system, content creators who want to protect their intellectual property, privacy advocates who champion individual rights, and regulators who must establish appropriate policies. The benefits span ethical AI development, legal compliance with copyright and privacy laws, risk mitigations for companies developing LLMs, and increased public trust in AI systems. Finally, let me highlight the four key takeaways from this project. First, compression metrics effectively detect LLM memorization with at 11.3% better compression for memorized text and statistical significance at p-value less than 0.01. Second, informational theory principles apply to neural networks. Classical concepts like K complexity, Shannon entropy, and perplexity remain relevant in the deep learning era, with strong correlations ranging from 0.38 to 0.83 confirmed empirically. And third, adversarial testing validates our approach, showing 39.5 times greater sensitivity for memorized content and distinct behavior under perturbation that differentiate memorization from learning. Fourth, we provide a practical, scalable methodology that requires only inference without any training and is applicable to any large language models, regardless of architecture of size. So this is the final thought. Let me conclude with three final thoughts. Compression reveals structure. Structure indicates memorization. The diagram illustrate this pipeline. Compression analysis leads us to identify structure, and structure in turn indicates memorization. As LLM continue growing in scale and capability, with models now exceeding hundreds or billions or of billions or even trillions of parameters, understanding the boundary between genuine learning and mere memorization becomes increasingly critical. We cannot simply trust that bigger models are better. without understanding what they have actually learned versus what they have memorized. This work provides quantitative foundations for what understanding for that understanding. We offer both theoretical insights connecting classical information theory and modern deep learning and practical methodologies that can be deployed today for privacy auditing, copyright protection, and model evaluation. And this is a summary of a contribution. And these are the references. And thank you for your attention. And I would be happy to answer any question that you may have about the methodology results or implication of this work. Again, my name is James. I'm from the Department of Electrical Engineering and taking the course for Computer Science and Information Engineering at National Taiwan University. You can reach me at my student email. Thank you.